This is the last session of the day, today being Wednesday. In case you were wondering, today is Wednesday. We're going to do 3 presentations today. The first one is going to be done by Garret Reese, which is going to be a process GC monomer analyzer, followed by Argon as an alternative to helium in process GC using EPD technology. And then the last presentation will be advancing real-time process measurement in the oil and gas industry. Our first presenter is Garret Reese. He's from Wasson. He is a process application chemist with a bachelor's in chemical and biological engineering. And he has worked with gas chromatographs for 13 years. This work has included servicing all types of GC instrumentation and GC detectors. And he's applicated several GCs both in the lab and online. He's helped design instruments and sample systems, different process sample types, and in different process environments. And Gary enjoys hiking and camping with his family. All right, Gary, please come on up. I'll set you up real quick.
All right, thank you.
Use this one. There you go. Perfect.
All right, I want to thank Victor for the introduction, and I also want to thank ATC for putting on the conference and allowing me to present for today. What I'm going to present is a paper on online extended refinery gas analysis using a process gas chromatograph with capillary chromatography. What we were looking at was a need for online or process GCs that have to continually control our processes. This is mandatory and necessary in the hydrocarbon processing industry because we want to maintain, the product that we're creating. We also want to maintain any possibility of catalyst poisoning, and we just want to keep our processes moving through each stage properly. Many of these applications require process GCs with broad analytical scope. One size does not fit all in the process GC world. Because of this, we need multiple detectors running simultaneously. We do have advanced GC technology. There's capillary columns. There's precise repeatable temperature programming. And there's precise repeatable pressure programming. Why do we think we need this on our process GCs? Well, because if we look at our lab GCs, which have been used all the time to analyze our process on our product, we see in the lab, we see capillary columns. We see precise repeatable temperature programming. We see precise repeatable pressure programming. When we send a sample from our process to our lab, that sample is probably injected on multiple different detectors, multiple different GCs that it needs to go to. The downside with using the lab is it has really excellent chromatographs and it has the multiple detectors. But we have to get that sample to the lab. When we're pulling sample, we're adding variability into our sample itself. Is it pulled the same way? Is it stored the same way on its transfer to the lab? Is it analyzed? Is there a way for our lights? Are they volatilizing while the sample transports? Are the heavies condensing? If we could get this same type of chromatography into a process GC, we're going to have more accurate data and we're going to have a better idea of what our process is actually doing at the exact time that we take the sample. The downside with this is that what we needed to decide on was first is how we were going to get a capillary column into a process GC. To do a capillary column, we need to have a convection type oven, just like you find in a laboratory GC. This convection oven needs to be able to temperature ramp, but it also needs to be able to handle the fact that we're going to put it in a process GC out on a process line. What we came up with was a design that is machined so that it can be the same every single time that we have it. It's fit to the shape of a column so that only the column is going to be heated. It also has a shape in it with a fan to allow continual convection around the column, allowing it to be heated consistently around the whole column. With capillary columns, if we have any cold spots or hot spots, it's actually going to adjust the way the chromatography looks. We also needed to design how we were going to make everything work. We needed EPC controllers, electronic pressure and flow controls. These electronic pressure and flow controllers need to control the forward pressure, allowing the sample to flow down the columns properly. We also needed to get back pressure and mass flow controllers. With back pressure and mass flow controllers combined, we actually create a split inlet, just like you would see in a laboratory GC. This allows us to reduce the amount of sample on column. Using capillary columns, we don't want too much sample on the column. You can overload the column. Detector gases also need EPCs because we need to ensure that we have the right flow of gases going to our detectors so that they are functioning properly. EPCs also allow us to have a gas saver mode on the instrument. It's out in the process, it's running 24/7. If we can limit the amount of times that a six-pack needs to go out to an analyzer, we can help keep it up and running for a longer period of time. This design also, because we're sending it into hazardous environments, needed to be rated for Class 1 Div 2 or ATEX. It needed to be designed to be out in the elements, so water resistant, NEMA. We went with a purged enclosure because now that we have a heated column and heated detectors, now we have ignition sources. So because we're going out into the process plant, we have ignition sources. So now that we have those heated zones, we went with a purged enclosure to ensure that we could still heat that column and heat all of our detectors without giving an actual ignition source being outside in the plant. We also needed a remote injection system. So we ended up having a sample system that's unheated that can be out in the plant in the hazardous area to take fast loop samples to ensure that we have a fresh sample each time before we sample. Next, we wanted to check the performance to see how this was all going to work and see if it was going to work properly. Two parameters are especially important with capillary columns. We need retention time stability. With our retention time stability, this is going to ensure that we're actually identifying the proper components on every single injection. We also need on-column sample amount repeatability. The amount on column is what we use to quantify and decide how much is in the sample itself. With inconsistent on-column amounts, we're going to have inaccurate sample amounts being reported. So our first performance test that we tried was to take a sample that included C1 through C11 hydrocarbons, injected at multiple times over 2 days to calculate the retention time stability. Our second performance test that we did was injecting the same sample onto a capillary column via our split inlet that we have multiple times to calculate the area count repeatability. These were going to tell us whether or not our design and our temperatures were right to actually give us data that was consistent. So on the left-hand side here, you can see what our microconvection oven is actually doing while it's heating. It's more of a clamshell, so we close up the microconvection oven, so while that element is heating up, it's actually sealed up inside the insulation. When the element actually stops heating and we need to cool the column back down to where it started from, the clamshell will open up. This allows us to use purged air and the fan to cool that column back down to its initial starting point so that we can inject the next sample. The data up top shows our retention time reproducibility. We have our methane, our C5 through C11, along with retention times that we had over 2 days. From the retention time, you can see we had 0.5% RSD across 2 days as about our max that we had between all the components. The reason we ended up doing this whole spread of components is, as you can see from methane, methane on a capillary column is a completely unretained compound. Because it's unretained, this is going to show whether or not our back pressure and our mass flow controller, working as our split inlet, are actually staying consistent over multiple days. Because the methane is only going to follow those pressures and flows, we know that this value, which is our 0.3% RSD, shows that our EPCs and our split inlet are functioning the same way throughout 2 days. With our pentane, hexane, heptane, and all the way out to C11, what these compounds are showing is whether or not our new convection oven we designed was actually having consistent heating. As we work up in our hydrocarbon carbon count, we're gonna need more temperature for it to elute off of the column. As you can see from pentane, pentane is the higher compound, so this one needs heat, but it doesn't need a lot of heat to elute from the column. It has a slightly higher percent RSD. Whereas as you go later and later, we had to heat up and heat up and heat up that column to get the heavier hydrocarbons to actually elute. That heating and showing that those retention times are actually stable throughout 2 days shows that we had consistent heating on that column every single injection. And we knew that that column and our insulation that we used for the oven itself was not retaining heat, and it was actually reading the right temperature so that we got the same elution time from each of those compounds. Next, we had our second assessment, which was our peak area. With this one, we used our methane. Again, it's unretained, so this is gonna show some of our biggest fluctuation off of our split inlet using our back pressure and our mass flow controller. Over 12 injections, we had a low percent RSD, showing that our split inlet, our back pressure controller, and our mass flow controller were functioning together properly so that we had consistent injections. With gas chromatography, we're using our peak area and a known concentration to calibrate our instrument. If we can have consistent peak area, we know our calibration is accurate. With consistent peak area and knowing that it's going to be consistent, then we can correlate that peak area to an unknown concentration while the instrument is running. Now that we had an idea that the microconvection oven was functioning properly, we wanted to do a case study to see what happened when we threw at it as much as we possibly could. So we wanted a sample of refinery gas. We wanted to analyze hydrogen, permanent gases, and hydrogen sulfide, along with also analyzing C1 through C20. To do this, we needed those multiple detectors. We need 2 FID detectors. One FID detector is going to look at hydrocarbons in the C1 through C7 area and get really good separation on that. The other FID is going to look at hydrocarbons from the C8 to the C20 area and have good separation on those. We're using 2 TCDs. These are both running off of pack columns that are in isothermal ovens. So inside our box, we ended up throwing all of these detectors, which is heated zones for 2 FIDs. We have slightly heated TCDs. They don't need to be as hot as the FIDs. We also had 2 microconvection ovens. One microconvection oven containing 2 capillary columns, the other microconvection oven containing only a single capillary column. We had 2 isothermal ovens, one of them containing 2 pack columns and the other one containing, or 3 pack columns and the other one containing 2 pack columns, with a total of 8 columns. So now our box had as much heat as we were ever gonna shove at it we have purge control, so we wanted to make sure that if we want to put this out in a hazardous area and it's purge controlled, that purge isn't affecting the way that microconvection oven was functioning. And also now we have extra heated zones to make sure that we're not overheating and causing issues with the chromatography. For the first FID for the 2 capillary columns, we actually used a backflush to detector setup with a valve. So the sample is injected, it goes down through the first column. The first column holds up our C8 plus components, and the lighter components are allowed to go onto the second column. Once the lighter components that we want to analyze are on the second column, we reverse the flow in that first column and backflush the C8 plus as one lump sum to the detector. The lighter components, C1 through C7, are allowed to elute and give us our separation that we need, and those go straight to the detector. The second FID, using the single capillary column in the microconvection oven, does our C8 through our C20. This oven, since we have 2 separate microconvection ovens, in your laboratory, you would have to use 2 different samples. You would have to have one oven program for the hotter sample and another oven program for the colder sample. Since we have 2 separate microconvection ovens, we're able to start the second microconvection oven at a higher temperature, allowing it to get through the C20 at a faster pace. The 2 isothermal ovens, one of them is holding up, and we're going to use a backflush to vent after our hydrogen comes off of the first pack column. Once the hydrogen comes off, we backflush the column and all the heavy components go out to vent. After that's done, our second isothermal oven comes in with another sample injection, and that one has a first column that separates our permanent gases from our CO2 and our H2S. Once the last permanent gas has made it off the first column and onto a second column, we use a valve bypass that allows for the CO2 and everything to bypass that second column and go straight to the detector. This allows us to then release the permanent gases, and those go towards the detector. In the sample system, this means we've got 1 sample going through 4 injection valves. Each injection valve can be its own sample amount, depending on which column we need, which lower detection limit we're looking for, and what's going to be best for the separation of all these different analytes. So with our TCDs, we actually decided to combine the TCDs so that all of your permanent gases come out in one chromatogram. So as you can see, you have helium coming out first, then our hydrogen. Right after the hydrogen, you're going to see a dip. That one is the valve switching to backflush the rest of the heavies. What we see in this and what we saw from our retention time repeatability, this is why we need consistent retention times on the isothermal ovens. With backflushing, if that hydrogen peak moves due to poor pressure control, then there's a chance that that valve dip is going to cut into that hydrogen peak. With consistent retention time, we know that that valve actuating at that exact same time every time isn't going to cut into the hydrogen peak. After the hydrogen peak comes out, next we see our CO2, our ethylene, ethane, acetylene, and our hydrogen sulfide. Those all come out in one group. And again, there's a disturbance right before the CO2. That's the valve injection of that train going through its pack columns. There's also another spike that you see after peak 7. That's the valve switching back in to allow the column that was being bypassed to bring our permanent gases back out onto the detector. Again, since these are timed events with valves, we need consistent pressure programming and flow control to ensure that our peaks are always coming out in the exact same spot. Otherwise, there's a chance that those peaks move around in our chromatogram. If we can keep them in the same spot with pressure and temperature control, we can analyze and consistently quantify the peaks of interest. After that valve switch brings the other bypass in, then we're going to see our argon on our oxygen composite, our nitrogen peak, our methane peak, and at the end we have our CO peak. With this one, we do have about a 250 ppm lower detection limit on the TCD for hydrogen sulfide. We have about a 10 ppm lower detection for hydrogen and nitrogen. CO2, judging by our data that we gathered, we have an LDL of about 200 or 100 ppm. When we look at our chromatogram for our first FID, this is the one that backflushed our C8 pluses to the detector. As you can see at the very first peak, that number 1, that's just a composite peak of all of our heavy peaks. We don't actually have to quantify it because we do have that second detector. So this isn't just a lump sum to where we send it off to process control and say, well, you've got this many ppm of C8 plus. We don't know if it's 50 ppm of C8. We don't know if it's 50 ppm of C9. This is all going to be resolved on our second FID using our second microconvection oven. As you can see from this chromatogram compared to the one before it, the peak shape is a lot cleaner and a lot smoother. This is on a capillary column using our temperature-controlled microconvection oven. We have really sharp Gaussian peaks, allowing for us to see the separation, as you can see in peak groups 8 through 11, with our acetylene, our isobutane, propadiene, and normal butane. We're getting good separation and good resolution. If we were on the packed columns, by the time these are coming out, it's harder because they're wider peaks to keep them resolved and keep good quantification on them. This chromatogram goes all the way out through our benzene with speciation across with the olefins and the alkanes. On our second FID that was on our second microconvection oven, you can see a large lump up front. This is all those light hydrocarbons that we don't care if we're quantifying on this detector because we quantified it on the other detector and we speciated it on the other detector. This detector, we're more worried about that octane through the C20. As you can see, because we started at a higher temperature, in this detector, this benzene and C7 weren't coming off the column till about 20 minutes. Since we have a separate microconvection oven that's at a separate hotter temperature, we're able to elute the C20 by around 25 minutes. So with this 3 chromatograms combined, we're getting that whole list of analytes out within about a 30-minute time period, and a little bit less than that. Then we just have to wait for those ovens to cool back down so that we can start the next injection. So with every injection, every 35 minutes or so, we're able to send off data giving all of these analytes information to the process. The FIDs, LDLs, we're sitting at about 10 ppm on each FID. So in all, what we found was that we were able to control our pressures, our flows, our temperatures, multiple detectors, multiple ovens at the exact same time and get consistent quantified peaks with good separation, good resolution. This allowed us to have all of this in a single analyzer, which helps to reduce some of the cost per data point shown. And that's all I have. Does anybody have any questions? Yeah.
Yeah, chromatogram with the combined TCDs,
Yes.
and it contains all the typical carrier gases. So what did you use as a carrier gas here?
So for the helium and hydrogen, we're using nitrogen as the carrier gas on the TCD. That way they have a different thermal conductivity and we can get the hydrogen quantified. For the carbon dioxide through the carbon monoxide, we're using helium. We've also tested it out and we can use hydrogen as the carrier gas on that TCD and get good response for all of those peaks. So since we're using 2 separate TCDs, we can use 2 separate carrier gases and actually get the thermal conductivity right for that whole spread.
I guess what threw me is that there's a single chromatogram for
Yep,
two
so we take the
densities.
two signals and we actually sum them together into one signal so that you get just a flat chromatogram with both different carrier gases.
Okay, I see. Thank you.
Yeah.
Well, you mentioned that you're using temperature class T2b. Is that the maximum you're going to, not higher to T2 or T1?
T2B is about max that we go to right now. We've done a few where we can get to T3, but right now we've stopped at T2 to begin with.
So T3 and T4 is not possible?
No, not with the T4 for sure. We've been working on getting T3.
Okay, thank you.
Yeah.
Any more questions? All right, thank you, Garret.
Thank you.
There you go. Thank you. All right, thank you, everybody. Now we're going to hear from Marc-Antoine Langevin. Yep. And Marc is from AS Devices. He's the application director with a PhD in chemistry from Quebec. And Marc joined AS Devices in 2018, where he is now the application director. Over the past years, he's worked on method development and for multiple applications in the field of fuel grade, hydrogen, air separation, food and beverage grade gases, semiconductor, and other high purity or specialty gases. Marc enjoys fishing, hiking, and video games and music. Thank you, Marc. Let me set you up here. Okay.
Hello, so thank you for the introduction. This is a plan of my presentation. I'll start with a short introduction, then I will present some of the application that we developed using Argon carrier and the EPD technology for the analysis of high purity gases, and some conclusion. So there are some very common detector in the field of process GCs. For example, you would have the TCD, which is a very common detector, but not really sensitive for application in the field of high purity gases. You also have detectors like the FID and the PID that are really sensitive to hydrocarbons, but they cannot measure the permanent gases, which are key impurity and high purity gases, with the exception maybe of CO and CO2 that you can measure with a FID, but you need to use a methanizer, which can be costly and require a lot of maintenance. You also have detectors like the FPD for, that are very specific to sulfur and phosphorus compounds, or ECD that is a very sensitive and almost universal detector that you could use, but it requires a radioactive nickel source, which is not very convenient for worldwide distribution or for end-of-life disposal. But still, with all these detectors, there's one big advantage is that you have a broad choice over the carrier gas that you can use, while in the case of, for use in process analyzers, especially for high purity gases, they have many inconveniences, such as limits of detection or being limited to some specific classes of compounds. So over the last decades, one of the detectors that have been the most used in process GCs for analysis of high purity gases has been the PDHID. that relies on helium. This is because the PDHID uses a very specific photoionization mechanism to ionize the impurity that reached the detector, and then the impurities are being measured from an electrode. So it's basically a kind of a universal detector that has a limit of detection of around 25 ppb for most of the impurity, which is quite interesting, but with this type of detector, you are being limited with the use of helium as a carrier gas, and as we know with the situation over the past few years, helium sources are becoming less and less reliable, and the prices are going up and down, so it's always interesting to have alternative solutions. Now, there's another type of detector that is also quite sensitive for limits of detection in the high ppb limits of detection, which is the BID. So it works with the same principle as the PDHID, but instead of having an electrode that is directly inside the plasma discharge, the electrode is protected by a dielectric barrier. So this detector requires less maintenance, which is interesting for process analyzer, but you are still limited to the use of helium as the carrier gas. So in the 1990s, Yves Gamache introduced the plasma emission detector, or PED, in the field of gas chromatography. And instead of using a photoionization mechanism from helium to ionize the impurities, it actually used the carrier gas, and it goes inside the plasma chamber, and when the impurity reach the detector, they are being ionized, and we measure light emission from the impurity that are ionized inside the plasma chamber. So then you can put some optical filters in front of the photodiode that measure light emission, and this optical filter can be universal or specific to the impurities that you're going to measure. It's a plasma that is generated by DBD, so there's no need for electrode maintenance. And this technology can reach limit of detection of about 1 to 5 ppb for most impurity in helium discharge. And since it is not being using this photoionization mechanism that relies on helium, you can use other carrier gases like argon, nitrogen, and neon. But still, this technology from the 1990s suffers from some drawbacks. For example, you can only record one wavelength at a time, and also you have no access to the optical module, so it's kind of a black box that is not configurable, and maintenance of the optical components is not possible. Here you have an example of, at the top, a clean argon plasma, and then at the bottom, light emission from nitrogen in the argon plasma. So you can see that if you want to measure nitrogen, you can select some wavelengths that are specific to nitrogen and be really sensitive to this compound. But due to some of the drawbacks of the PED technology, in 2017, AS Devices introduced the plasma emission, the enhanced plasma discharge, or EPD, which can now measure and combine up to 4 different wavelengths at the same time, which is going to allow new measurement method that I'm going to present in a few minutes. Also, we introduced some electron injection and stabilization electrodes to improve the signal-to-noise ratio and therefore improve the limits of detection. So now we can reach sub-ppb limits of detection using helium as the plasma discharge gas, but we can still also reach low ppb level limits of detection using argon as a carrier gas. And also something that is that might be interesting for you is that this technology can also be integrated on almost any third-party process or laboratory GC on the market. And here it's just a slide to show that with the incorporation of our additional electrodes and high-quality electronics who are able to stabilize the plasma discharge and therefore reach much better limits of detection compared to the original plasma emission detector. Also, we want to note that the GC platform that was used for all the tests that I'm going to present is the IMOF platform from AS Device. But as I mentioned, the EPD technology can also be integrated on almost any third-party platform, laboratory, or process. So there's no problem with that. And also a quick note on the GC valve that was that we were using for these tests. We were using the PLSV technology from AS Devices, which is a purged valve that is frictionless, so it can be used for over 1 million actuation, even in UHP application. So it's a very good valve for process application. And since it's a frictionless valve, it can be sulfonyl treated, which is especially important for application that requires highly reactive molecules like sulfur compounds or even for moisture analysis. And now we actually just released a new form factor for the valve that is now 100% retro-compatible with third-party systems. So this valve technology can also be integrated in third-party GCs. So now for some applications that were developed with the EPD technology using argon as the carrier and discharge gas. The first example I would like to present is quite simple. It's actually the measurement of permanent gases in argon. So here you have a standard chromatogram that was acquired for simple injection on a molecular sieve of 10 ppm permanent gases. But this result highlights the importance of the GC valve that was used because if the valve is not leak tight, then you would definitely have some interference from air on the nitrogen and oxygen peak. So having a valve that is leak tight is definitely important here. And another example here is for 2 ppm permanent gases in hydrogen. And to the right, you see the ISO standard for fuel-grade hydrogen. And you can see that for all the permanent gases, even using argon as the carrier gas, we can reach the limits of detection that are required for the permanent gases in fuel-grade hydrogen. But here we had to use a hard-cut configuration. And it's interesting to note also that using a similar method with the hard cut, we could also use the same method to measure the permanent gases in the other permanent gases or helium and argon. And here you have a table that summarizes the limits of detection that were acquired for a standard 0 to 20 ppm range permanent gases. So you see that for all the compounds, the limit of detection is in the 1 to 20 ppb limit of detection, which is already performing better than the PDHID that only relies on helium as a carrier and discharge gas. Another key advantage of using argon as the carrier gas in this application is that for most application in the ultra-trace level analysis, for the measurement of oxygen, you would actually measure oxygen plus argon because they coelute on most GC columns. So using argon would remove this interference from argon that would coelute with oxygen because it's going to be hidden by the carrier gas. And it's interesting to note that over the years that we have been doing this test, so many times, we realized that actually when you measure argon plus oxygen, the amount of argon is often overlooked and you might have actually more argon than oxygen. So if you want to have a very accurate oxygen analysis, it's interesting to go with argon as the carrier gas. Another key application that we developed would be crude argon analysis. I'm not going into all the detail, but it's a very important application in the field of air separation for improving argon recovery. And it's the measurement of trace nitrogen in a mixture of argon and oxygen. And typically, you would have a setup like this one with a long GC column and even an oxygen trap, because it can be quite difficult to separate trace nitrogen from oxygen. But thanks to the fact that we can measure and combine multiple wavelengths, we can do what we call spectral compensation, and therefore make a more simple system with a short GC column and only the detector at the end. So we can remove one column and one valve to have a faster analysis for the crude argon analyzer. And here, actually, what we show is why it's important. Here you have actually a result from a universal detector, and you can see that it can be quite hard to separate the nitrogen from oxygen here. So why we developed the spectral compensation method to have this fast analysis is that we can measure two different wavelengths, one that is highly sensitive to nitrogen, and the second that is only sensitive to the background level. And what we can do is we can combine these two wavelengths to get the red chromatogram here, where we compensate the baseline to get a clean peak from nitrogen that can be easily integrated. And here you see some linearity data, and it shows that from 0 to more than 500 ppm, the nitrogen reading is going to be linear, and this is regardless of the oxygen-argon ratios, because the spectral compensation is going to compensate for the oxygen concentration. And here are some repeatability data that were acquired on a 4 days period with an injection every 30 seconds. So it shows that this method is actually very stable and repeatable. And also, again, this is a result that highlights the importance of the valve that was used, because we have now multiple units on the site that have been used for over 3 years with injection every 30 seconds without need of maintenance for the valve. And since we were able to do this test, people who implemented this system have been able to improve their argon recovery by 3 to 7%, which is very interesting considering the cost of argon on the market at the moment. Also, another example here is the use of the EPD technology to measure light hydrocarbons and CO2 without the use of a methanizer. So, as mentioned earlier, CO2 can be measured by FID, but you would need a methanizer, and also the FID would require additional UHP, hydrogen and air to generate a flame, while here the carrier gas is also used as the discharge gas. Also, this example here was acquired for moisture by GC, and for this application we had to use a water call 1910, which is a very specific column from millipore sigma, and we were able to reach 0.1 ppm limit of detection for moisture with the use of a vacuum pump at the end of the detector. And this is much more sensitive than what have been done by other companies that use the TCD for measuring moisture with this column, who showed the limit of detection around 0.05 to 1% limit of detection. And one advantage of argon carrier compared to going with helium is that the system is going to stabilize much faster compared to helium, because moisture has a strong tendency to stick in the tubing. So going with argon, you can stabilize the system in less than 1 day compared to argon that can take almost a week to completely stabilize. Here are other examples of matrices that were tested for moisture analysis. So here, hydrogen and also oxygen and nitrogen and CO2 that were tested. And we even tested this method with ethylene, and it's actually a very interesting method for measuring trace moisture in petroleum mixture. We also tested some noble gases like krypton and xenon, and we can reach 15 ppb limits of detection for xenon and 100 ppb for krypton, which can be an interesting application for the air separation industry, as these two gases can accumulate in the argon production. Also, N2O and SF6 that are contaminants that can be concentrated in the production of noble gases like krypton and xenon because they are at very low concentration in air, so you have to accumulate a lot of air to produce krypton and xenon. So you will also accumulate N2O and SF6. So it can be important to measure these compounds, and you can do that using argon as the carrier gas with limit of detection, again, that are in the ppb level. Also here, example for BTEX, which can also be measured by PID. Actually, the PID is a very good detector for the BTEX, but you have to change the xenon lamp every 1 or 2 years. While in the case of the EPD technology, there's no need for maintenance in the long run. So it's also an interesting alternative. And the final test I wanted to show is total sulfur in CO2, because there's a Coca-Cola standard that requires less than 0.1 ppm total sulfur in food-grade CO2. So we can measure H2S and total sulfur actually in CO2 down to the ppb level without any issue. Here, other chronogram with a mixture of sulfur compounds and light hydrocarbon, and just a graph that shows that in the case of methyl mercaptan and actually all the other sulfur compounds, we actually have a linear response and repeatable response in the ppb level for all the sulfur compounds that were tested. And conclusion, the EPD technology is highly sensitive even when we use argon as the carrier and discharge gas, and can be integrated on almost any third-party GC platform. So that's about it. And maybe also a note on the PLSV valve that was used, that plays an important role in the results that were shared, as it's a long-lasting valve that can be used for these applications. So, thank you.
Anybody have any questions for Marc?
Yeah.
Yes, I have a question. The EPD looks like a really interesting detector, and is it suitable for deployment directly in hazardous areas?
Could you repeat the question, please?
So the EPD, right?
Yeah.
Is it suitable for usage in hazardous areas that are explosion protected?
Actually, it's one of the best solutions because, for example, in the case of oxygen production plants, they don't want to have hydrogen on site many times. So we have been requested to use the EPD technology on oxygen plants to replace FIDs because they don't require any hydrogen or any additional flammable gases. So it's actually quite a safe detector.
Right, but we have to show, as for example, process GC manufacturers, that our instrument is certified to be used in Class 1, Division 1 or Division 2, or ATC Zone 1 or Zone 2.
Well, I would say in the case of our gas analyzer, like the IMOF platform, the K8000, at the moment when we want to work in hazardous environment, we put it in a purge cabinet.
Okay.
But we are working on a full heavy-duty process GC platform for the future. But the EPD technology itself is quite safe, and it's just a plasma discharge. It's not anything burnt. There's nothing burning. There's no flame. There's no high voltage.
Okay, thank you.
Thank you.
Thank you, Mark. All right, we have one more presentation. This will be the last presentation of the day, given by Todd Ratajczak. Thank you very much. With JP3 measurement, Todd has a BS in chemistry, MS in analytical chemistry, has over 15 years experience in the process analytical industry with a long-standing focus in spectroscopy and gas chromatography, GCs, has been with JP3 Measurement for over 4 years as their product manager, and he enjoys spending time with his 2 small children.
There we go.
Thank you, Todd.
Okay. Do I just move forward here?
This thing's invisible.
Yeah, I know. It can be hard to track.
And there's the pointer right there.
Oh, okay. There we go. All right. Good afternoon, everybody. My name is Todd Ratajczak. I'm product manager at JP3, and today we're going to be talking about our presentation, Advancing Process Measurement in the Oil and Gas Industry with Raman Spectroscopy and Cloud-Based Data Management. And that is a mouthful. So what we're going to be doing is I'm going to give you a brief introduction and some context of why we're talking about what we're talking today. And broadly, this is a two-parter. I've got a section talking about the comparison between Raman spectroscopy and NIR spectroscopy with the obligatory, principle of operation and background, and how we did that test and what conclusions we can draw from it. And then the second part is going to be talking about our cloud-based analyzer monitoring solution, which, with the addition of Raman analyzers, we have made into a fully analyzer-agnostic monitoring solution in the cloud. We're going to be talking about how that collects and handles data, the cybersecurity concerns about it, and some example features and applications thereof. So, who are we? What are we doing? Why am I talking about Raman and NIR spectroscopy? So, our company is JP3, and since 2015 or so, we have made NIR spectrometers for the oil and gas industry, and we got our start in the midstream space with gas processing, pipeline batch interface detection, condensate stabilization and vapor pressure control, that kind of thing. Doing all of that with our NIR spectrometers. And recently we've started interacting more and expanding into the upstream and downstream industries as well. And with expanding your applications also comes a need to expand hardware capabilities. So we started, if I got a laser pointer on this?
It should be on there, but
I don't know. Yeah, okay, it's good. Anyways, you can see at the left here that the Verax system is our primary near-infrared spectrometer. It's an online process, near-infrared spectrometer, and measures hydrocarbons in real time. It's great stuff. And that technology is what we've been using since 2015. And recently, we've come out with another near-infrared spectrometer, and another near-infrared spectrometer, and a Raman. So one of these is not like the others, and one of these is very new to us, the Raman. So, I was very interested in putting these two technologies on the same process and comparing them and seeing what kind of conclusions we can draw. Is one obviously better than the other? Are there downsides? Are there upsides? Let's take a look. Then the other core part of JP3's business is providing a cloud-based analyzer monitoring solution with SCADA integration. And we call this system Viper, and it's a cloud-based web application that by default, all of our analyzer products have a cellular modem in them, and everything uploads data to the cloud, and then from this cloud-based web application, users can view their analyzers, view the data on their analyzers, view history, and all kinds of stuff. And we've been developing this for many years, developing and iterating it over many years. So, it's got a whole bunch of features, very intuitive to use. And, we can use this to do things like, in this example, generate a performance report to validate the analyzer's functionality and accuracy. So, like I said, obligatory principle of operation slides. And I know I know you guys have seen probably some variation on this a couple times so far today, but please indulge me. So Raman spectroscopy is a technique used to observe the vibrational, rotational, and other low-frequency modes in a sample. And what that means is that you shine a powerful laser onto the molecules in a sample of interest, and most of the light will not be affected. Some of the light will be scattered without any, it'll be scattered without any wavelength shift at all, and that's called Rayleigh scattering. And a very, very small proportion, like, 1 in every few million photons will have a shift. The frequency of light will be shifted. And if the wavelength is increased, that is Stokes-Raman scattering. And if the wavelength is decreased and a higher energy photon comes out, then that's anti-Stokes scattering. Most Raman measurements use the Stokes-Raman scattering because that is much more common. All right, and then you can also see here NIR spectroscopy, near infrared absorption. It uses the same kind of physics of light interacting with molecules, but it's different. And I've got one more slide on that. So Raman spectroscopy, yeah, we're looking at the Stokes-Raman scattering where light is scattered from a molecule with a shift in the wavelength of that light, and you can collect that and create a spectrum of scattered shifts of light of that wavelength. So Raman spectroscopy is a very common chemistry, a very common analysis method in chemistry to provide essentially a molecular fingerprint. And if you've got a whole bunch of different species in a sample, like, let's say, for example, gasoline, each individual component is adding its fingerprint into that spectrum. But the fingerprints are all, kind of like, that's why we call it a fingerprint. All the fingerprints are individually unique. So like most all spectroscopy, Raman spectroscopy is non-destructive. It requires minimal sample preparation, and it can be used with solids, liquids, or gases. Raman is very common in pharmaceuticals, material science, nanotechnology, food and beverage. It's all across industry. But it hasn't been as popular in the oil and gas industry, but that's starting to change. So we talked about Raman. Now in IR, near infrared spectroscopy. Again, this is a light, we're using light to measure something. It's a spectroscopy method, but the fundamentals are a little bit different. With NIR spectroscopy, what you do is you shine light through a sample. You're not scattering light off of it. You shine light through a sample. You have a detector on the on the other side of your sample that collects the light that is passed through. The sample absorbs a certain amount of the infrared light. That's called absorption. So from the amount of light that is received at your detector, you can calculate the amount of absorption at a given wavelength of light. And you do that across a spectrum of wavelengths, and you get a near-infrared absorption spectrum. And the nice thing about this is that you use the Beer's law essentially that you can calculate the concentration of a analyte in your sample. And the really nice thing about Beer's law is that the concentration of your analyte is directly proportional to the amount of light absorbed, which makes calculating these things a lot easier. Of course, when you have multiple components all together in a sample, your spectrum ends up with a whole bunch of individual absorption spectra lying on top of each other, so you can get some very complicated absorption spectra with complicated absorption features. So what we do to analyze that is modeling it with algorithms as chemometric modeling. And you can also model physical properties because a lot of physical properties are a consequence of the composition of your sample. So those can be modeled too. So how we calibrate spectroscopic analyzers, both Raman and NIR analyzers, is with chemometric modeling. Chemometric modeling following ASTM D8321. And how we do that is you take a spectrum with your spectroscopic analyzer. You get a spectrum of your sample. You collect that sample in the appropriate sample container, and you take that to a lab. You have that measured in the lab with a primary method. In this example, we're using GPA 2261 for the composition of a gas. And that provides you a laboratory value. So we have a primary method laboratory value and a spectrum of the sample. We can combine those together and generate a chemometric calibration model that predicts what the composition or property of interest is in that sample. And with ASTM D8321, it says that we need 30 to 50 calibration references to build a robust measurement model. And we want to make sure that those 30 to 50 samples are chosen across the full range of variation of the process. So if you've got, if you've got a crude oil sample and the vapor pressure in that process happens to range from 6 psi to 12 psi, well, you want to make sure you get, you get those extremes, you get some samples in the middle, so you're measuring the full variation of the process. So again, we're talking a little bit more about comparing and contrasting Raman and NIR spectroscopy because we're looking at both here. And I think a Venn diagram is always helpful. So, if you've got an online measurement, application that you need to have measured and you would like a real-time online measurement technology, Raman and NIR are both certainly options. And we can, and we can look at and see sometimes NIR might be more appropriate, and sometimes Raman might be more appropriate. And then there's some instances where it's a toss-up. They could both work almost equally well. So, and this is my opinion. Feel free to disagree with me, but I have thought about it a bit. But for NIR, crude and heavy condensate, diesel and jet fuel, I would say NIR spectroscopy is a good option for those measurements. Because with with strongly colored or black, in the case of crude oil, samples, Raman measurements show a whole lot of fluorescence. And fluorescence is when your laser light hits the sample and the light is scattered back at a longer wavelength. But it's not the Raman kind of scattering. It's a different mechanism, and it interferes with the Raman spectrum. And there's easily ways around that with pre-processing the spectra and all that. But it is a source of noise, and interference that if you can avoid it, you might as well. So heavier, darker colored hydrocarbons, I think, is an easy. NIR probably makes more sense there. And then for Raman, an interesting thing about liquid phase near-infrared spectroscopy is that dissolved methane has a really indistinct infrared spectrum. Methane itself has a well-characterized infrared spectrum in the gas phase and in the liquid phase. But dissolved less than 1% methane has just a really indistinct infrared spectrum. And that's just not the case for Raman. It's a different technology, so you can see it just fine. So for something like a, natural NGL or Y-grade fractionation, where you're looking at demethanizer bottoms, for example, and you care about the percentage of dissolved methane, that's a great opportunity, application for Raman, where with an NIR analyzer, we'd probably want to be vaporizing that sample. So, that's where Raman makes sense. Also, aqueous samples. Raman is the natural choice because near-infrared, water absorbs near-infrared light very, very strongly. So it can be extremely challenging to do an aqueous measurement with a NIR spectrometer. So Raman makes sense for something like an aqueous sample, like amine, like an amine CO2 and scrubber. And of course, anything that's not hydrocarbons, Raman makes a lot of sense for, because there are a lot of common non-hydrocarbon molecules like hydrogen, nitrogen, oxygen, that are either not near-infrared active or very, very weakly near-infrared active. That it would just make a lot of sense to do a Raman measurement instead. So where you get overlap is measured fluids like gases, natural gas liquids, gasoline, extremely light condensate, and chemical processes. Those are kind of the things where NIR could work and Raman could work. So I wanted to see how they compared. So in this example, what we did here is hooked up a Bruker Superflux Raman spectrometer, which Bruker is the company that we've partnered with to provide Raman spectrometer solutions. And we used a Mark-Metrix flow cell Raman probe because that's what I had on hand at the time. But we've got that hooked up just immediately in series on a fast loop with a with a JP3 Verax near-infrared spectrometer using the JP3 Verisight NIR flow cell. So both measurement points are on a fast loop. We're measuring gasoline, and they're directly in series with each other. So it goes, just around like that and gets returned to the process. In the question and answer phase, if anyone can point out what is horrifically wrong with this setup, I will give you bonus points. Okay, so more about this this test. The NIR analyzer that's there, it's a very long-running near JP3 analyzer. It's been running for about more than 5 years on that fast loop. It's sampling a midstream gasoline pipeline that's mostly carrying conventional and premium gasoline, and sometimes it's got natural gasoline and naphtha, and broadly it's a gasoline quality measurement, making sure that the product that's in there meets specification. As you can see in the picture, the Raman analyzer probe was installed immediately downstream of the NIR flow cell, ensuring that the samples were, that one sample would represent the spectra on both analyzers from a given timestamp. And then just, we connected the Raman analyzer to what I call a system hub that allows it to connect to the cloud, just like the NIR analyzer. And both analyzers are measuring API gravity, distillation profile, Raman, anti-knock index, V over L, and DVPE on this measurement point. The Raman analyzer was initially calibrated using process samples, offline in a lab, and they further incorporated live samples during the test. And the NIR analyzer used a calibration model that's been iterated over the past 5 years, essentially. So both of them had complete, robust calibration models. And the chemometric modeling that we do, it uses MATLAB with PLS Toolbox. The models all follow ASTM D8321, and all the models use partial least squares regression. So here's some results. For DVPE, these are validation plots, and what you're looking at there is the x-axis is the laboratory measurement, so that's what a sample taken to the lab says, and the y-axis is the prediction from the analyzer. So on the left side, that's what the y-axis on the left side, that's what the Raman predicted. The y-axis on the right side is what the NIR predicted. And ideally, all of your data points would line up exactly on the x equals y line, or y equals x line, sorry. But of course, nothing's quite ideal, but everything here lines up in that general area. We don't have any crazy outliers. We don't have any, curvature in the overall trend. It's pretty linear. And you can tell that there's a lot more data points for the NIR because, of course, again, that's been operating for 5 years, so we just have a lot more data in the data set for it. So overall, here's just a selection of samples and the deltas between the measured value and the predicted value. Overall deltas for the Raman, 0.22 psi. For DVPE, that's again difference between the laboratory and the analyzer value. And for the NIR, the average delta was 0.35 psi. And I would argue the absolute value is what matters, not whether it's above or below, because that's essentially random. So little bit of a difference, but not a huge difference. For API gravity, we get a similar view here that everything clusters around the y equals x line, and we don't have anything crazy going on. And for DVPE, our delta for Raman was 0.33 psi, and for NIR, 0.32. I mean, that's almost exactly the same performance. If anybody has, there's another way to interpret that, if anybody wants to think about it and bring it up in the Q&A section, but I would say these are extremely similar results. So, what I would say here is, in this particular example, near-infrared and Raman spectroscopies perform about the same. I mean, there's some difference there, but we're not looking at a factor of 2 or an order of magnitude difference in performance. It's relatively minor. I mean, although the Raman had only been running for about a month, and the NIR analyzer had been running for about 5 years. And it's not like the more effort you put into developing a calibration model, the better it will get ad infinitum. You're eventually going to, asymptote out at a certain level of performance that's essentially in line with the accuracy statement of the primary method. But we were able to, another way to put that would be, we were able to get the Raman analyzer with a model as robust and accurate as the NIR analyzer, with the Raman doing that in a month and the NIR analyzer in 5 years. So that suggests that making a robust Raman model could require fewer samples and be able to be done quicker and with less effort compared to a near-infrared analysis. But overall, I would say, like I showed in my Venn diagram chart, I would argue that Raman and NIR are complementary technologies. There's areas where NIR makes more sense. There's areas where Raman makes more sense. And in something like gasoline analysis, where you could do either one, you really could do either one. I think it comes down to cost, non-performance-based considerations like, cost, maintenance, things like that. So now that JP3 has a Raman analyzer that we are offering, we've updated our analyzer monitoring and data management platform to account for that, and kind of, somewhat organically, just in the process of that, we ended up making a fully hardware agnostic data management platform, because we took out it's required to be a JP3 analyzer and everything's programmed for it to, talk to and assume that there's a JP3 analyzer in the mix. Now it just can talk to any analyzer. It's still designed for spectroscopic analyzers like near-infrared, NDIR, Raman, FTIR, an analyzer that produces a spectrum, but we can also use non-spectroscopic analyzers like, gas chromatographs. That spectrum can be a chromatogram instead, or even analyzers that don't have either, like a densitometer or a flash meter or a vapor pressure analyzer. So JP3's been working with customers in this data management platform for years and years. We've gotten lots of feedback from our customers on things they like, things they don't like, things they want to see. So, I would like to tell you just some of the features and requirements for a robust data management platform. And again, this is my opinion. Feel free to, if you would like to disagree or have other thoughts, I would love to hear it, honestly. So, how do we get data into the cloud? The first step is we collect our spectral data from the analyzer. And in our system, we process that data at the edge. And that's an Internet of Things kind of term. That means that we have a relatively powerful computer at the analyzer that can analyze the data, or analyze the spectrum, analyze whatever data we have with it, and package it up to be uploaded to the cloud in an efficient manner. We're not just streaming raw data into the cloud. And then, we publish that data up to the cloud via an Internet of Things network, essentially. So getting processed data from an analyzer in a site, which within the fence line in a processing site, up to the cloud requires requires a extreme focus on cybersecurity, because nobody wants to increase their risk profile any more than you absolutely have to. So yeah, cybersecurity is always a primary consideration. And of course, JP3 analyzers don't just talk to the cloud, we also talk to customer DCS and SCADA. All of that is air-gapped. So talking to the DCS or SCADA system, you got Modbus, OPC UA, MQTT, RESTful. We can do analog outputs as well. And then talking to the cloud is a separate private APN network. And a private APN is essentially it's an agreement with a cellular carrier to create essentially a private data tunnel just for our devices. So the benefit about this is that if you're not using a private APN, your devices are essentially exposed to the public internet. And before we had a private APN, that's what we did, and we just had extremely thorough firewall rules. But again, that's a risk that we can avoid. So we moved to a private APN. We've got agreements with AT&T and Verizon. So if you get a better AT&T signal, we use the AT&T APN. If you've got a Verizon signal, we use the Verizon APN. But the benefit I love about it's open source, it's scalable, so we can add additional carriers if necessary. So basically gives you a dedicated data tunnel that has no exposure to the wider internet. There's no exposed IP addresses, and all of the data is encrypted end to end. And that gets your data from the analyzers into our cloud. And then from our cloud, we've got to ingest the data we've got redundant cloud infrastructure. Everything's backed up as one would expect. And we use Apache NiFi, which is an open source solution that was developed by the NSA. So again, focus on security and reliability here. But we use Apache NiFi to transform the data, all the data that we're getting, into a coherent format that can get put into what we call a data lake, which is like a database, but I've been informed that it's not a database, it's a data lake. There's some kind of difference. I don't actually know what it is. And then as this data is coming through, we can set up notifications for users, and we can set up notifications for users to get text messages or emails for critical events. So once the data is in the data lake and users can look at it and interact with it, what can you do with the system? We can create custom dashboards to look at multiple analyzers at a time. We can zoom into individual analyzers and individual issues with interactive data visualization. And we can, everything is remotely manageable. And broadly, you can have secure access with multi-factor authentication and permission-based architectures. So yeah, here's just a default. Here's a default dashboard that you can scrub through a timeline of an analyzer's results, and you can see there's a spectrum and a process map. The process map is just the first two. These an X and Y axis of the first two principal components. So very straight, very helpful for the chemometric side of things. It also just looks cool. And yeah, so you can scrub through your data, scrub through a timeline, compare different data trends. It's very powerful and genuinely very intuitive. I was able to use it pretty proficiently within a couple of weeks after starting at JP3. We've got custom dashboards. You can look at you can set up dashboards for individual analyzers or whole groups of analyzers. So you can have a dashboard for all your analyzers in your plant at once, and and you can check the status of all your analyzers. And again, we're not talking just JP3 analyzers. We're saying all analyzers in a plant or in a unit, and you can check on the status of all of those in 5 seconds compared to 30 minutes walking around and checking every physical system. As a spectroscopic-based system, we put a lot of emphasis into sample management. Every analyzer has samples that can be associated with it, and these samples have a lot of, samples are barcoded, so you associate a sample with an analyzer at a certain timestamp, and you have a whole bunch of data that is also, can also be stored with that. You got histories of samples, when are samples being taken? Are they good samples? Are they bad samples? And we can turn all that sampling into performance reports for individual read points and analyzers and say, hey, look, the samples are matching up, and everything looks good, or the samples do not match and something's wrong, and we can look into it further. So I've got, very, very quickly, almost done. We've got Viper in the control room. We can take Viper from the cloud, put it in a physical server in a control room, and basically this customer's data does not leave their fence line, and it goes straight to their control room, and we have a dashboard. This is a crude distillation system that, that provides real-time data of what's going on in their crude tower. And we've got Viper installed on a touch screen out on a pipeline. It's on a terminal, at a pipeline terminal, and similarly, we're taking data from an analyzer and trending it at what they call the cut shack, where they have the controls for this terminal, and they're looking for when the one product stops arriving. You get transmix, the mixture between two products in a pipeline, and when the transmix ends, and you get pure product for your second for the next one. And that gives them real-time data on their product transitions. So there we go. Very brief conclusion. We've taken a Raman spectrometer and a near-infrared spectrometer and compared them on the same, right next to each other on the same measurement. And I would argue they have broadly comparable performance, at least for vapor pressure and API gravity, which are the ones we drilled down into. This test suggests that Raman models can achieve similar performance with fewer calibration samples, which may means reduced development overhead longer term. And with a Raman analyzer, we've turned our our kind of JP3 specific data and analyzer monitoring web app into a fully hardware agnostic cloud-based platform for an entire plant's worth of analyzers that users can view and manage their analyzers and data in real time, from the cloud anywhere, from your house, from your vacation in Florida, wherever you need to go, you can always pull up your analyzers on Viper. And we have a carefully designed edge and cloud architecture with a focus on cybersecurity, allowing our users to have, genuine real-time monitoring in the cloud. So there we go. We can very quickly do some questions. If anybody thinks of something later or has another question or anything else, I put that there. I really do like to talk about analyzers and chemistry. So, feel free to send me an email. I've even put my cell phone up there. If anybody has a text message, that'd be great. So, all right, thank you very much. Yes, go ahead.
I have a quick question.
Yes.
Is your MATLAB running in the edge or in the cloud?
The method runs on the edge.
MATLAB.
MATLAB.
Yeah, for chemometrics.
Right. Yes.
Is that running in the edge computer or in the cloud?
We use MATLAB, we use PLS Toolbox in MATLAB just to generate the model.
Okay.
Once the model is generated, it's a file that gets stuck on the edge computer, and the edge computer then runs the model. So, it is in the cloud. We use AWS, but yeah, we use MATLAB just for generating the model via PLS Toolbox.
Next quick question is about,
Yeah,
you
go ahead.
mentioned about taking advantage of IoT network. And is that you actually use that network transmitting spectra into the cloud?
Yes. We have an IoT framework essentially because every one of our edge computer devices has a cellular modem. So it's kind of direct from the cellular modem to the cloud.
Right,
Does that make
thank you.
sense? Okay. Feel free to ask more later, or if you want any. Okay.
So could we purchase this software? Is this something we could?
Yes. Yes. So the way we've done it in the past is, if you buy a JP3 analyzer, you get the software. But now that we've made it hardware agnostic, yes, you can buy just Viper without having to buy any hardware. So yeah, that's no problem at all.
Hi, Todd. I'll try to make this quick. So if you look at the emission spectrum from Raman, the Raman emission spectrum and the Rayleigh scattering emission spectrum, do they overlap? Is it the same bandwidth, so to speak? I don't know what the right term is, but...
Oh, okay. So so is your question, like if you have a NIR spectrum and a Raman spectrum of the same thing, would there be interference?
Correct. And then how would you distinguish between the Raman emission and the...
That's a very good question, but there is no overlap, or basically they're two fundamentally different things. You would not have interferences in either way. The short answer is no, there's no interference, there's no overlap. A Raman emission spectrum is fundamentally different than a near-infrared absorption spectrum, mostly because of the magnitude of the effect. Like I briefly mentioned, the Raman effect is approximately 1 in every few million photons. So, if you shine 100% of laser light onto a sample, what you get back is it's genuinely a few parts per million of your incident light intensity. So what we use for Raman is a CCD array, essentially a camera sensor that is extremely sensitive. And what we use for near-infrared spectrometry is a strained InGas detector, which is effectively 1 pixel of the multiple megapixels of the CCD you need for Raman. So, it's a factor of a million, a factor of a couple million in difference of intensity. So you're never going to see interferences between a Raman and an NIR measurement.
Awesome. Thank you.
There we go. I might have over-explained that, but sometimes that happens.
Todd.
Okay. Did I bring anything up? I didn't bring anything up. Oh, thank you very much.
Thank you, everybody. Please don't forget to fill out your scorecard and turn them in to Paul. And that concludes today's session.